Okay. So as you can see my screen, this is the entire architecture of LSTM. Okay. So I will go through, just I wanted to show that how LSTM look. Okay. And I'll go through one by one. First, let me show you the difference between LSTM and RNN, the both diagrams. So you can see it here. One second. Yeah. If you can see this diagram, let me zoom it a little bit. You can see this is RNN, this is LSTM, this is GRU. So you might notice that this is more simpler, this is most complicated, and this is little bit simpler than the LSTM. This architecture, this is little bit simpler. So why I chose to explain this LSTM, because once you understand this LSTM, no, you will easily surpass this RNN part, because this unit is itself here. You can see here, so that will get covered. And here, if you'll say nothing is different, is little bit here in this section it is different. So I'll explain this part also, but let's focus on that LSTM. So I think you guys remember about the yesterday that what I told, that the hierarchy about RNN, LSTM, GRU, transformers, which includes encoder, decoder, and then the attention. So what exactly that? Now here, let me ask two things. So Mitra, are you a little bit aware about the neural networks a bit? Okay. So let us suppose here I have three input. Okay, three input, and here let's suppose we have, now this will, the connection will look like something this. The connection will something look like this. And if let me make here, so if, and this is called the input layer. Okay, input layer, this is called hidden layer, and this is called the output layer. Now hidden layer can be any number of times, like this is called the one hidden layer, this entire part, this is one hidden layer. It can be multiples, okay, like 2 3 4, and in every hidden layer it can be the any number of neurons. So this is called the neurons or perceptron, you can say. Okay, and this is the input layer. In input layer, it depends on your data, it could be any number of values here, like. And in output, again, it depends on your requirement, it can be any number of neurons. So that this output layer is also a kind of a hidden layer. Why it is output layer? Because after that there is a no layers. Okay, this is the finally we will get after this. Now what these all are, if you seeing this line, what these all are, this is actually called the connections between the, from this neuron to all these neurons from the first hidden layer. So this neuron from all the neurons from the this hidden layers. So this is actually called the weights. Okay, so I'll not go too much depth in the weights, that how it got assigned and update. So the rough idea is, if you have a three input layer and the uh, four output layer, so usually it will be, the total weight will be 3 yes 7. So here the weight will become, one second, one second. Input is, you can see now here three neurons, hidden layer is four. no no so so this one will become 4 cross 3. So there will be total 12 weights are there. 4 cross 3. Okay. So because if you will see here, if I will just remove this. So you can see this is weight 1, this is weight 2, this is weight 3, this is weight 4. And the same way 4 weights for this all connection, 4 weights for. So total 4 into 3 dimension 12. And for every neurons there will be one bias. So there will be 4 bias. So the between these input layers and the hidden layer there will be total 16 parameters, and these are called the trainable parameters. Trainable means which need to be trained or which needs to be updated. Okay. And in this neuron there are multiple activation layers, activation functions are there to introduce the non-linearity in your network. So there are multiple. So the what it is required as of now, as I said in the last class, to go through that, one is sigmoid and the other is tanh. So and the softmax also I said, but as of now these two you can see. So the output of the sigmoid will be always between 0 to 1, and the output of the tanh between is to -1 to 1. Understand? Means if you will give any input to this tanh function, any input, it will either give you the output is -1 or 1. I mean between that. And the sigmoid, anything input you will go give to the sigmoid, it will give the output between 0 to 1. Understand? So now let's see this here, the LSTM. So part has missed. Now let's see that how let me build up on a completely a box, nothing neurons and anything in that. Hmm. Yes. So this equation, if I would tell, let me then give you the brief. So assume this is one neuron. Okay. So this one part is called linear. Understand? It has the linear, and here it is non-linear. So this is the input. This is that. And there is a one bias. There is an one bias. Let's suppose the input is 10 here, and what would be the output? So how output will get calculated? So the linear is, let us suppose, linear formula is mx plus c, and let's suppose non-linear is here some sigmoid. Sigmoid is denoted by this, or you can write it like this. So assume it like this. Can I write the combined two both like this? Because whatever the linear will go, that will go into the non-linear part. Okay. So this linear, it is going as an input into the non-linear, right? This function. And here this is the bias. On place of c, let's write here b, and x is what here 10, and these are the two trainable parameters m and b, which needs to be trained by using the back propagation. And whatever the initialize, so there are a lot many different weight initializers are there by which we initialize some value of m and b. This is called weight and bias, and this is called the trainable parameters. So that is got trained it in back propagation to get the minimal error. Okay. So this is on the high level, but if you need it to be that complete go through the neural network, then again I have to prepare a separate. In that I can explain the depth that how neural network exactly works, okay, with each and every weights and how it get updated. Okay. But this is the high level. When I'll say the neural network, every neurons will behave like this. And in terms of the non-linearity, if I'm saying sigmoid, means in its non-linear sigmoid is there. When I'm saying the neural network with tanh, it means in the non-linear part there is a tanh function is there. Okay, this is what I mean. Now, so let's see this. So here this is, let us suppose a normal neural network. So the reason behind why the RNN or the LSTM got needed when we had already ANN, artificial neural network. The reason behind, let's suppose here the sentence is, my name is Ved. Okay. And I am, one second please. Okay. Now, okay guys. Okay. So if there is a sentence, my name is Ved and I'm having two, and I have two mobiles. So you can see this I is related to Ved, right? So there isn't some sequence, some dependency. Now, in terms of ANN, what it exactly happens? So understand this connection. This entire sentence, no, it goes directly in one shot to the network. It does not keep the information with the sequence. That was the issue with the normal neural network, dense neural network, or you can say artificial neural network. Then the researcher introduced RNN, recurrent neural network. So this one was earlier a ANN, but what they did in RNN, they added one feedback loop. So this is your input, this is your output, and this is called here your feedback. Now what does it mean by feedback? So let's expand this RNN. Let's expand this RNN. So when I'll expand, it will somehow it will look like this. So this is here H0. Okay, and here let's suppose this first word is, let me write first here, these are H1, H2, H3, H4, and here your Y hat means the output. Okay, Y hat is the output. Now the first word is, my name is Ved, and if suppose the word will be like this, and this is all the RNN unit. So this is one RNN which I am expanding. So what it is doing, when I RNN is not only the neurons, it has the neurons, but I'll explain that what exactly inside the RNN. Just I'm giving on a high level first to understand its workflow. So yes, this is neuron definitely, but with some other calculations as well. So if suppose I'm giving an input to the neuron here, this RNN my. So what it will do, so understand this one I have just expanded. Okay, this RNN only I had just expanded it here. So my, and then after there is, you can see this one state, this hidden state is going, which I showed it here. The same it is going to the RNN part. And when the next word is going here name, in that one more input I'm taking, which is from the my. And then when I'm giving the word is, it is taking another input H2 which has the information from my and name. When I'm giving the input Ved to the RNN, it has the input H3 which has the information of my name and is. So you can see here it is able to conserve the information of the text as well, the previous text as well. How it is able to do that, that we will try to understand the mathematically from the LSTM. Okay, so this is the how structure, but these things were not there in the ANN. It was directly taking all the sentence and giving the output. That's it, by converting into the vector and then doing the linearity and the non-linearity. Okay, so now LSTM RNN has what the issue. Let's suppose for this type of a smaller sentence, it is able to gather that. But if suppose the sentences are of 8, 10 or 12 line longer text or the sentence, and if this sentence word has the relation with this last word of this sentence, it was not able to do that. So in a mathematical term, we say it as a vanishing gradient issue. Okay, so that again we will try to understand in on a separate, but as of now understand there wasn't some vanishing problem with the ANN, because of that this issue happened. Okay, now in LSTM what happened, so this is the RNN. Okay, but if I just draw the basic small, let's suppose this is the LSTM. Okay, this is LSTM, this is input, this is output, this is input, this is output. So there was one feedback loop in the RNN. Okay, one feedback loop, and there was now in LST they introduced another loop in LSTM. So this is called long term memory, and this is called short term memory. So what does it mean by that? Why they did? They wanted that from any sentence, from any given sentence, what things I need to remember or what things I need to forget. So what should be the short term and what should be for the long term. Okay, so this long term which you are seeing it here, that is let me write in blue here. So short term is denoted by HT and this long term is denoted by CT. Okay, this is called cell state and this is called HT is called hidden state. Okay, is it clear till here? And wherever I will write XT, that means XT means that is the word input at that specific time. Okay, so when I'm saying my name is, so here when I'll talk about that word name is going, it means this is the XT at time t which word is going. Okay, so this is out and this is the previous one and so on. Okay, so now let's understand it on the LSTM part. HT is called hidden state, CT is called cell state. HT means short term memory, CT means long term memory. Yes, cell state, and HT is hidden state. It is cell, CELL, and this is called hidden state. You can say cell memory or hidden memory. Now, these are the two parts wherein uh, component in LSTM. Earlier, this was there in the RNN, but this was not. Okay. Now, let's see the LSTM part. You can see it here. Whatever I told, if you will see, this CT you are saying CT and CT minus 1, HT and HT minus 1 are same. HT minus 1 is just the previous for the previous time stamp, and CT minus 1 is the previous time stamp for the cell state. See that cell state, long term memory, short term memory, HT minus 1, this is called a hidden state. Sir, make on mute. Okay. So this is now there are few assumptions we have to understand. Okay. So there are, if you can see it here, this LSTM. Let me delete this neural network part from here so that I can. Okay. Now, so there are few assumptions we need to. So wherever these boxes are there, no, these kinds of boxes, if you are seeing it here, this box, this box, this box, this box, these all are neural network. These all are the neural networks. Yes, you can see here I had written short-term memory and this is the long-term memory. Okay. XT is the word at that current time which we will feed into the network. Let's suppose there is this sentence, my name is Ved. So now I want to see the computation for the word Y. So Y, it means word my. So this my is going at the XT. So this is the value for the XT. Okay. Sumitra, have you understood what I'm trying to? Okay. So wherever you are seeing these boxes in this network, this box, this box, this box, and this box, these all are the neural network. Okay. Now, apart from that, you would see two, three things. This cross, if you can see it here, this one. Yeah, I will come on that. Yes, these are the sigmoid. This is the cross one. You can see it here, this here, and the other is here. You will see plus this sign. Okay, and here one you will see tanh. So these four things you need to understand very carefully. So this first is neural network. This is called matrix multiplication. This is the matrix multiplication. Okay, be on mute. And this is called matrix addition. Matrix addition. And this is actually, you can say, this is also the pointwise multiplication, and this is just a pointwise tanh conversion. So whatever the value will come, let's suppose there is a value 5, so it will pass under the tanh function 5. So whatever the value of tanh 5, that will be the output after this. Okay, so this is the four things we need to understand. Is it clear till here? Okay. This block diagram, okay, I haven't explained yet. I'll come on that. I'm just deleting it so that I can write it near to this. Yeah. Let me pause it. Okay. So now, attention. Yes, because until unless you will not understand this transformer and understanding the transformer and attention, because after this I'll make you guys understand that how embedding works, how to train the embedding. Then only you will understand how transformers get trained. Okay, the vectors got generated. Okay, so that is very most important than that. So now this part is clear. Let me change the color of thread. Okay. Now in LSTM there are three inputs. You can see here three inputs in LSTM. what is ct minus 1, ht minus 1 and xt. You can see here these are the inputs, ct minus 1, ht minus 1 and xt. This is the input, three inputs, and there are two outputs, ct and ht. Two outputs, so we need to connect all these dots. Okay, just understand it step by step. ht and ct. Okay, there are two. Now what we are supposed to do in the LSTM. So whatever we are seeing it here in the entirely LSTM, and what exactly this part do. So actually we actually update the cell state in LSTM. So this is the only task it performs, nothing else. That how to update the cell state, and which one is cell state? This straight line, this one which you are seeing it here, because this is the output will come. So how to update the cell state, and the second thing, how to calculate the hidden state. How to calculate the hidden state. So because this one we will calculate, no, on basis of that the cell state will get updated. Okay, so this is how the LSTM work. Okay, this is the how we perform the mechanism inside that, what exactly it will do, how it will do, I'll come on that. Okay, the now question is how exactly this point 1 and point 2 are there. These are the mechanism which happens inside the LSTM, which it performs those all blocks we saw. So how this point 1 which I'm saying that we actually update. So if we just try to expand this point 1, so what exactly do, so based on given xt, based on given xt, what need to remove from ct minus 1. Please mute yourself. What need to remove from ct minus 1. So how cell state will get updated. So whatever the input word will go to the LSTM, this one you can see here, whatever the input word will go to this LSTM, this ht minus 1, based on that what we are supposed to remove from this cell state. Okay, so right now I know you guys won't understand that what's in ct minus 1 is coming. So now let me give an here brief. So you just understand there are multiple LSTM blocks are there. This is one LSTM here, this is one LSTM here, and whatever the ct is that, no, this is the input for the next LSTM. Whatever the ht is there, no, that will be input for the next LSTM. So you can understand this is like that. I showed you that block diagram, no, there are two inputs, feedback loop. So this is, so whatever the output will come, no, that will go as an input for the next word. Are you getting my point? I will come, Sumitra, I'll come. I'm just giving you. We'll go step by step, slowly. Again, you will understand it like that. When suppose there is a sentence, how are you? So for the how, this entire mechanism will go. whatever this two output will be there, that will be input for the word R, and then xt at that point of time will be R. Okay, so this is how it go. Okay, now, so that's what I wrote here. Based on the given xt, what need to be removed from ct minus 1 means if something is not important, then we need to remove. Okay, and the second, based on the given xt, if from your sentence, if nothing is, if you're from cell state, if anything is not important, that part need to remove. Okay, based on given xt, what need to add to the cell state. Okay, that's it. Yes, the cell state will be the filtered version from your hidden state. Whatever the input you will give, that will be that. Okay, yes, input is the xt, and and whatever the xt and ht, you can see it here. This is the ht and this is the xt, and the combinations of both here, every time it is going to the ct, and between that there are some mechanism is happening, this one, this one, this one, this one, this one. If, yes, ht minus 1 is input, ct minus 1 is input, xt is input, that I said it here in the first line. There are yes, ht minus 1 and ct minus 1, the both are the feedback input, and xt is your actual word. Okay, now is it clear till here? Okay, just give me a minute. Sorry, those entire thing were not get recorded when I was explaining. Okay, but anyway, you understood that how exactly it works. Okay, so now we understood forget get, why we use the forget get. Okay, now let's see the input get. Okay, so input gate, what it exactly do? So this one is the input gate. So now it is clear for the forget gate. I'll come on the backend part as well, more depth. But as of now, understand this what is going. It is multiplying with ht minus 1. Here this is ht minus 1. Concatenating both the vector, it is passing through the sigmoid based neural network, and it is giving some output, and that output vector is multiplying with the vector. So this all ct minus 1 is a vector, ht minus 1 is a vector, xt is a vector, ht is a vector, ct is a vector. These entire things, everything which you are seeing, that is not a value, those all are the vectors. And when I'm saying a vector, it means it's a combinations of the numbers. And what would be the dimension of this vector, that we will understand it soon. Sorry, I didn't get your point. Mhm. No, this is fixed. This is the LSTM architecture. This is not going to change. Okay. Now the input gate. So the input gate, it decide based on current input. So current input is xt. Based on current input, that in long term, is what? Ct minus 1, or you can say ct, whatever it is. In long term input, what new information should be added, should be added. So what was the task of forget gate? To remove something if it is not important. Or what is the task of input gate? To add something, right? So that you understand. Now let's understand the output gate. I'll come on the architecture again. Okay, so in output gate, based on your current input, based on current input, which is xt, it decide that what need to show. It decide what need to show. What need to show in a long term memory is the finally, okay, is the final output. What it decide what need to show in long term memory. Yes, long term memory, which is ct, and it also create your final hidden state, which is short term memory. That is, you can see it here, the architecture in this out here, whatever it is, you can see here, this is input. So here the final ht and ct, how it is doing, those all part. This one ht, this is final ht or final ct. Okay, how come this will become the output? I said it just before, that which you are seeing it here, this one will become the input for this. That's why here it is ht minus 1 and this is here ct minus 1. That's why whatever the input for current word, this architecture you just missed again. I think you are not able to connect the dot. See it here, this is ht minus 1, this is ct minus 1. So whatever the output will come, this is all the architecture of the LSTM. Two output came here and this one goes to the feedback. This is for the first time of the word hello, and with for this word hello we will get some ct and ht. Now the next word is how. For this is the same architecture, I'm just building it here. Now for this ct and ht are ct minus 1 and ht minus 1, because these are for the from the previous word, and we will get here again to ct and ht. This one will be the input for the word r, and the so on, it will keep on moving. Now only we need to understand how this ct and ht are getting calculated. That's it, LSTM solved. Clear? Okay, so let me pause the video and delete those here, and then we'll cover closer to that diagram. Now let's understand that. So which you are seeing it here now, this is called ft. Here in forget gate, this is the output of this sigmoid, we will say it as an ft. Here this one we will say it as an it, this one we will say it as an ct, the output of the tan h, and this output is it, and this one is called ot. This sigmoid output is called ot. Now this now here we need to understand this ct is called no candidate's memory. Okay, this I'll come on. Output of this sigmoid network is called it. Okay, input gate, so that's why it is input gate at time t, candidate gate, so output of this candidate cell state at time t, ot is the output at the time t, ft is the forget get output at the time t. Okay. Now one thing here, very important, and please keep in your mind this statement which I'm saying. Dimension of ht and ct will always be same. Dimension will be same, not the value. Means if ht has a dimension 3 cross 1, then ct will be also 3 cross 1. Okay. And these all are the vector ht, ct, xt. Okay. And when I'm saying here ft, this is forget get output, and this it and ct, it is called input get output, in which this ct is actually the candidate gate. Is called candidate gate, and the ot is called your output gate. Okay. So these all above, whatever we saw here, ft, it, ct, ot, are the vectors, and dimension of this entire dimensions of ft equal to it equal to candidate cell ct and ot will be same. This all dimension. Okay. This all will be same. Now value will get calculated by the architecture. I'm coming on that. So might you would have get the intuitions as of now that when it is on sigmoid, when it is on tan h, so the output will definitely getting different. So for now, let's understand, and I'll tell you. Let's understand this candidate cell first. What exactly here? So there is an, you can see here. Sorry, this one. Let's understand. Let me delete this. So if you'll see here, what exactly at this part is coming, just focus it at this part, what exactly is coming. This is called matrix multiplication. If you would see this line, this cross is matrix multiplication, and what is multiplying it here? ft multiplied by ct minus 1. Correct. Now I'm saying ft is also a vector and ct minus 1 is also a vector, and both will have the same dimension. So as of now, let's understand. Okay, so here if you are saying ft and ct minus 1, so let us suppose the ft which we are seeing it here, this one, this ft, we know, or for anything, just pointwise operator I just want to show. If suppose ft value is coming 1, 2 and 3, so the pointwise operator means the each value will get the way matrix multiplications happens, no, like that how it will do. Okay. So and ct minus 1 is anything value 2, 4 and 6. So this one to this one, this one to this one, and this one to this one. And if it is here addition, if addition, so how the addition will happen? See that addition will get happen between ct minus 1, ct minus 1, and let us suppose if you are doing it with the fd, but it is not with fd, it will, the multiplication will happen between CT and IT. Okay, this is the multiplication, this vector, and whatever the output was the CT and IT, that will get added with the CT minus 1. Understand? So this is just a multiplication here. Here, this is the addition. No, first multiplication is with FT and CT minus 1, and here there is one more multiplication in input gate, which is CT and the IT, and whatever the output of this will come, that will get added with the CT, whatever the multiplication of these two will go here, and whatever the value will come here, that will pass from the tan h function, and whatever the output of OT will come, this two will get multiplied here, and that will be our final HT. And this, whatever the value will come from here, no, whatever the value will come here, that will go as a CT, and one part of that will multiply with OT, and that will be the HT. So what does it mean by this tan h? So this one, you guys might have understood this cross multiplication and addition. Here this tan h, so if suppose this is a vector of values 6, 4 and 8. So if I will pass into tan h, so this one will be somehow like this. This value will get changed like this: tan 6, tan 4, and tan 8. This is how it will get converted. Okay. These are the tan. So whatever the value for tan 6, tan 4, tan 8 will come, this vector will get converted into that after this operation. Whatever the CT will come from here, no, it will pass from the tan h and it will get converted, and whatever the OT will come, then it will multiply with this vector into the OT vector, and that will be the final output of HT. Is there confusion in this? Okay. Recurrent. Yeah, yeah, that's what I'm saying. No, this will go as an input until or unless, that is called the recurring. Recurring means continuously going. See, LSTM is a type of RNA network. Recurring means that something, if it is getting repeated. Let's start. So we understand this is the neural network, the box which it is showing it like in this structure, and this structure with sigmoid means the output will between 0 to 1, and if it is tan h, it will be from -1 to 1, and then this is the matrix multiplication, this is the matrix addition. That's it. Now if you have a neural network, the first, what will be the first questions will come in your mind, that this how many uh, nodes will be there in that network, or how many layers will be there in that network. Okay, so that is the question. So might be Kaushal sir and Aditya, if you guys would have ever done it and then hands-on, or remember when we were trying to build that LSTM any model, we were passing it something like that. LSTM and something here 50 or like this. We are passing. Okay. So this 50 is whatever we were passing. This 50 is exactly your number of nodes. Okay. And if suppose there is an 50 number of nodes for this, then it will be same for all neural networks. For this neural network, for this neural network, for this neural network, this is the 50. In one question, I need to clarify. I have a little bit of the doubt that how many layers will be there. Okay, for that network. I need to cross check in that part that how many layers will be there in every neural network. But nodes means neurons. This neurons. This is one, two, three. So if you will pass LSTM 50, means there will be 50 neurons. Okay. Yes. There are four neural networks. One neural network, two neural network, three neural network, four neural network. And in these all four neural networks, there will be 50 neurons. Yes, because in input gate there are two neural networks. Okay. Now, now let's take one sentence and I'll give an example with the sentence, which is called hello. Okay. And let's suppose this is a, and hello is what here? XT. Okay. And this has the four dimension. Okay. The dimension of this word XT is 4. So let's suppose x1, x2, x3 and x4. Okay. Now, if suppose this is 4 here, so this one will get input here and there is an ht minus 1 which is coming from here. So this both will get concatenate. So how it will, suppose this is one diagram for 1, 2, 3, 2, 3 and 4. And suppose we selected the nodes as 3. LSTM nodes as 3 we had selected. So this is the input for the hello. This is x1, x2, x3 and x4. This is the xt. And now if we, what I said, if we selected the node 3, then the dimension of this ht will also be 3. Okay. And the ct will also 3. Remember this part. Suppose we take the number node as 3, for that neural network, it means the dimension of ht minus 1 is same as the number of node and also the ct minus 1 dimension. Same. So here this is 4 for the xt, and if you see this line, only focus on this part. This part. Here what it is, one ht is going here and then xt. So this is this both, there is a no multiplication and addition. This is called concatenation. This section means I am trying to concatenate two vectors. Okay. So concatenation means, now let me change the color here. 1 2 3. And why I am taking 3? Because as I have taken the nodes 3, so this will be 3. So this is here h t minus 1 is 3. And for this neural network, how many nodes will be there? 3, because I have selected here 3. So let me build a neural network. 1, 2 and 3, and these all have the sigmoid, right? And how this connection will happen? Sorry. I said it, if suppose you selected node as a 3, then the dimension of ht minus 1 will be 3, and the dimension of ct minus 1 will be 3, and the number of neurons in this network will be 3. Okay, so that's why, yes, that's number of neurons. You can see here 3. In this neural network, the number of neurons will be 3, and ht minus 1 dimension is 3. And I said it, let's suppose for our vector, for our word hello, it has the vector of size 4. So that's why x1, x2, x2, that's why I taken 4. This all will be go input in this neural network. And that output will, yes, that's what I said. Not number of neural network, the number of neurons will be 4. Here it will be 4. So from the every neurons, we will get this output f1, f2, and f3. Okay, this will be somehow, it will denote it as like ft, which is f1, f2, and f3. You can see it here. This is the ft, and this will be the, again you can see it is having 3 dimensions as we had selected the nodes. So ft has also, now it comes up with the same dimension. Is it clear? Now here total 7, here 3. So the weights are here. Weight is 3 cross 7. Whatever the neurons are here, 3 cross 7, that is the weight. And the 3 biases for each neurons here. So plus 3 bias. So how many trainable parameters are there? 24. So just understand, if you select an LSTM for a 3 memory, for the 3 nodes neural network, there will be 24 trainable parameters only in the forget gate. Now we have this 3 neural networks are still left. Now, so this, now here what we'll do, whatever the ft has came, whatever this ft value has came, this ft will get multiply with the ct minus 1, which is here. See this part, whatever this ft is coming, that will get multiplied with the ct minus 1. And what I said, if suppose nodes is 3, then ht minus 1 and ct minus 1 will have the same dimension. So this ct minus 1 will also have the same dimension. Correct? Or any confusion in that, still you can ask the question. Okay, so now this is the equation for the ft. Ft is a sigmoid neural network in which this is the weights, whatever this 7 cross 3 and this value weights, which is the concatenation of ht minus 1. Ht minus 1 is that hidden state and the input xt, and plus with our bias. This is, you can see this is all ht minus 1 and xt are the hidden state and the xt. See this ht minus 1, ht minus 1 and xt, ht minus 1 and xt are the concatenation. It is going, and then the bias is there passing into the sigmoid, that is the ft formula, the same. And if you would see it here, what I said, this is 3 cross 7, and this entire is how much? 7 cross 1. You can see here, no, this is 4 and 3 7, 7 cross 1, and this is here 3 cross 1. So first, if you have to multiply this to weight into this concatenation. So if you multiply this, sorry, 3 into 7, not 1, because you can see now here 3 into 7. So 3 into 7, 7 cross 1, so it will become 3 cross 1, and you have to multiply this too. So if you multiply this, this one, 3 cross 1, and actually it will get transposed in that. So 1 cross 3, so it will become 3 cross 1. So this is how the ft dimension will come, 3 cross 1, which you can see it here. I had showed you. And that's what I said, that if suppose ft will always come between 0 to 1, so let's suppose 0.5, 0.5 and 0.5. Let's suppose this three value will come, this three value f1 f2 f3, 0.5, 0.5, 0.5, and c t minus 1, which is coming from here, which is coming from here. This value is having also three dimension, because as we have selected node, and it is 4, uh, 8 and 12. So if we will multiply ft into ct minus 1, 4 will become 2, 8 will become 4, 12 will become 6. It means we removed some information from this vector. Or if this word would have been important, this will come like 1, 1, 1. In that case, the 4, 8, 12 will directly go to the next. Now tell me, any confusion in forget gate? So if you understand it break by break, block by block, you can figure it out. Any confusion in forget gate? Okay, so the next proceeding for the uh, input gate and the output gate, we will cover. That is all depends on the your understanding, that how you want.